It's time to build our VPN topologies across the network, which is simpler than the transport topology. We'll test Layer 3 VPNs first. There are two general options regarding the VPN topology within the seamless MPLS design. The first option is using a central set of route reflectors somewhere in the core, such as CSR7, to be the central point of route reflection for all VPNs. You would first have to advertise CSR7's loopback into BGP labeled unicast so that the PEs could reach it, then form iBGP VPN sessions from the PEs to that route reflector. The second option is to follow the same iBGP topology we already built for labeled unicast. In my opinion, this scales better and is more intuitive. The L1, L2 routers will serve as VPN route reflectors in a hierarchical design, just as this second tier of route reflection uses BGP LU to interconnect the different islands. There is nothing interesting about CSR7's BGP configuration for these VPN v4, VPN v6, and eVPN sessions. The three L1, L2 routers are just route reflector clients, and all of the sessions are up. Let's head to CSR8 next. CSR8's BGP configuration isn't very interesting either, but there is one important caveat. While it is required to adjust next hops for labeled unicast routes in both directions, you should not modify the VPN next hops. From a control plane perspective, the L1, L2 routers are relatively transparent and should not swap VPN labels. For completeness, let's examine XRV13, the other L1, L2 router for this level 1 domain. There's not much to see here. We first initialized the three VPN address families of interest without any fancy options. Then, we activate the VPN AFIs towards the PE, identifying those peers as route reflector clients. However, when we activate the same VPN AFIs towards the upstream route reflectors like CSR7, we don't mark them as route reflector clients. Again, we don't want to needlessly reflect routes back to the core unless they originated from our local domain. Let's head to CSR5, one of the PEs, to review its configuration. I know you understand basic Layer 3 VPNs and VPN peerings already, but let's quickly review the full configuration as it relates to VRF UPF, short for User Plane Function. This represents a connection to the upstream router in a cellular network, whereas XRV11 connects to a cell tower. The VRF uses a basic any-to-any design by importing and exporting the same route target and is enabled for IPv4 and IPv6. There's nothing noteworthy about the PE to CE link, as it is assigned to the proper VRF and supports both versions of IP. Because it is not relevant to the VRF, XE does not display the VPN peerings to CSR8 and XRV13, but we'll verify that they are operational in a moment. We can see the eBGP connections within the VRF, connecting to CSR1's VRF UPF. Let's quickly confirm that all relevant VPN sessions are operational. We see two iBGP peers with CSR8 and XRV13, along with the eBGP peer to CSR1. CSR5 learns one route from each, so let's examine that next. Because CSR5 learns two copies of the VRF RAN route of 192.0.2.0/24 with the same RD, BGP picks the best route before importing into the VRF. That's why there's only one iBGP route in the VRF, along with the default eBGP route learned from the UPF customer. Just for fun, let's examine the details of the VRF RAN route using the RD and specific prefix. The details are almost identical between both routes, including the MPLS label, which was allocated by XRV11. Because the next hop is the same, it really doesn't matter which route wins, but the router chose the one from CSR8 because it has a lower BGP router ID. This is one of the late-stage tiebreakers used when comparing iBGP routes. If you took notes from the previous clip, you might remember that the transport LSP from CSR5 to XRV11 used a label stack of 16013, 93015. The VPN label of 91015 would be pushed first, with the other two labels on top. We can query the fib to confirm that, and I'll use the detail keyword to make the route recursion easier to see. Within the VRF, CSR5 has a VPN route with a next hop of XRV11, along with the corresponding VPN label. The path to XRV11 is via XRV13, introducing the labeled unicast label. The path to XRV13 is via XRV14, which uses the SR label. The full label stack will therefore be 16013, 93015, 91015. Let's head to CSR1 to ensure the customer has connectivity. Quickly checking the routing tables of both VRFs, we see that the routing exchange was completed successfully. This proves that our VPN control plane and hierarchical route reflection was configured correctly. To test data transport, we need to know the source and destination IP addresses. Loopback 15 is within VRF UPF and represents an internet host. I used Google's well-known DNS server just for fun. Loopback 111 represents the cell tower test endpoint, which exists within VRF RAN. Let's trace downstream from UPF towards RAN using the following traceroute command. As we confirmed on CSR5, the initial 3-label stack looks correct. This includes an SR label on top, BGP labeled unicast in the middle to stitch the islands together, and a VPN label that never changes. For additional practice, you can trace the LSP in the opposite direction and also explore VPN v6 connectivity. Going through those repetitions will make you more proficient with this architecture.